So today we're going to take a look at section 14.1. We did an activity related to linear measure, and now we're going to talk about linear measure as it relates to our common measurements as well as metric measurements. So to start with, linear measure refers to measuring in a straight line as with a ruler. A few facts that I know you know are that distance is never negative. The distance from A to B is the same as the distance from B to A. And that there are two primary measurement systems. English, sometimes called standard, or English standard. I heard it called common something when we were doing test creation for the current state licensure exam. I was part of the state licensure exam creation for middle school math. Isn't that cool? I was, and we talked about that particular word, like what should we go with for this word? And then, of course, the metric system. So we're going to start with the English system first. That's the part we haven't actually done anything with together, that is. Our English measurements that we use for length primarily are feet or foot, yard or yards, and mile or miles. Abbreviations, FT for feet, YD for yards, MI for miles. It does matter that you put MI for miles because we use M for meters. So don't abbreviate that one any shorter than that. Occasionally I have somebody put Y for yards. Just go with the two-letter acronym. It will be better. Okay, the two-letter abbreviation rather. Reminders, there's 12 inches in a foot. There's 3 feet in a yard. And either of these two you can keep. You don't have to necessarily remember both of them for uses. You could use them interchangeably. You can either remember that there's 1,760 yards in 1 mile, or there's 5,280 feet in a mile. The feet conversion is the one that I remember. That's the one that I probably learned first, is why I remember that one. And so I don't remember the other one whenever I need it at all. And I often will forget that this is 5,280 and I'll think 5,260, so it happens. But just be aware, those are your different measurements. So what I'd like to do is to show you now what it looks like to convert inside of metric. We saw an example, inside of English as opposed to metric. We saw an example written out last time about how convoluted it looked because you had to do all these sort of fraction bar looking things, but I didn't really explain it. So I want to explain how that works with some examples. So example number 1 is to convert 72 feet into yards. So what we're going to do is we are going to take that 72 and write down, 72 feet. And you can do this, visually speaking, how I have done it. I'll show you, and then I'll show you another option that somebody showed me last semester, which I thought was kind of clever, or maybe 2 semesters ago. It's been a little bit now. What we need to do is we need to get the feet to cancel out. So we've got to put feet on bottom, right? Numerator and denominator, they cancel. And I want it to convert into yards, and I do have a conversion that's straight, feet into yards. Now, the number 3 is probably coming to mind, and you need to make sure you put it in the right spot. Is it 3 yards is 1 foot, or 3 feet is 1 yard? Which one is it? Yeah, there's the 3 feet. So the 3 actually goes on bottom, and the yards, 1 yard goes on top. So let me talk about why we're allowed to do this. Because 1 yard equals 3 feet, I'm really multiplying by the fraction 1. These two things are equal measure, right? And when you put a number that's equal to something else on bottom, it's the same as the fraction 1. You guys know that, right? Like A over A is equal to 1, 5 over 5 is equal to 1. Well, 1 yard is equal to 3 feet, so that is equal to the fraction 1. So that's why we're allowed to do what I'm doing. The goal in doing what we're doing is that the feet cancel, which leaves us with the only unit of yards when we're done. And then in terms of computation, you would multiply across the top, whatever multiplication you had. This one's not very exciting. It's just 72. And then you would divide by whatever you had in the denominator, 3. So what is 72 divided by 3? Anybody with a calculator? 24, yes. 24. And it would be 24 yards. One of my classes in the past anyway, talked about having used this as a fence post. And so they drew it like this. they started with the 72 feet up here, and then they put their feet down here in their yards. And then we had my 3 and my 1. It's the same numbers, it's in the same location, but they structured it a little bit more rigidly, and they likened it to a fence post. Now you might look at that and think, what's the difference? Well, the more steps you have, the more difficult it is to do what we're about to do. I'm going to do one more example where there's just one calculation to do, and then after that I'm going to show you what it looks like when you have more than one calculation. So this example needs us to convert yards into miles. And there is a flat-out conversion, written down over here that you have that talks about the number of miles and the number of yards and how they're related. So this is a one-step process. I'll go ahead and draw the fence post for it just for fun. And I have 8,923 yards. So what will go on bottom of the next piece of my fence? Has to be yards, because I need the yards to cancel. And my goal when I'm done is to have miles, and I do have a conversion that relates these two, so miles goes on top. Where do these numbers go? This says miles and yards. What number goes where? 1 on the top, and the 17, what was it? 60, yeah, on the bottom. So of course the yards cancel. And then we would multiply across the top, again, not very exciting, 8923. And then divide by what's on bottom, 1760. And for the purposes of what we're doing, if you do have decimals that come about, that's okay. We'll use 2 decimals of accuracy. Okay, so if we round what you're getting to 2 decimals, what do you have? 5.07. And what are the units on this problem? Miles. Now, number 3 says that it wants me to convert miles into inches. And there is not a direct line of this chart that says miles on one side, inches on the other, right? But I could take miles and turn them into yards, or miles and turn them into feet, and go from there. So what we're going to do is we're going to have to do more than one step. So I'm going to draw, again, this fence. I've got the 37 miles on top, and just like on the last ones we've been doing, I have to put miles on bottom to get them to cancel. And now we get to make a choice. Sometimes we have choices and sometimes we don't. And the choice is, do I want to convert it into feet or into yards? Either one's okay. What would you guys like to do? Feet? Okay. Alicia, you seemed certain about that. Why did you really want feet as opposed to yards?
Because you have to do more conversions and put to yards.
Yeah, that's a very good observation. Because if you get it into feet on this chart, you'll notice there's a relationship between feet and inches is where I want to end up. So it's not wrong to convert it into yards, but if you do, you'll have more steps to do. So we'll convert it into feet, so miles into feet. So what number goes where? Right. The 5,280 is on the top, and what will go on bottom? A 1. Now, I'm not going to finish anything at this point. I'm going to keep going because this will actually cancel my miles, but it doesn't get me all the way into inches. Now I need a ratio that will get me into inches. So right now feet is on top, and I need it to cancel, so feet has to go in the denominator. And I'm wanting to turn it into inches so the inches can go on top. Okay? Now what ratio do I need to write down? What numbers and where? How are feet and inches related? Yeah, 12 on the top and 1 on the bottom. And again, we have feet then canceling here, and we're left with inches, which is our goal. That's what we want. And now I just have to do some multiplication. Now, interestingly enough, the division here is by 1, right? Denominators are all 1, so I don't actually have to do any division. But I do need to multiply 37, 5280, and 12. It's a big number. What do you guys get?
2,344,320 inches.
Yeah? Okay, very good. Okay. Any questions on this particular chart? Converting with it, that sort of stuff. Okay. So we're going to chat again. We've already done a lot with this, but we're going to chat more formally about the metric system next. The metric system is an international measurement system, very common, especially in science and industry, SI. So sometimes you'll call it it'll be called the SI metric system. We'll see the S and the I put in there. Multiples or fractions of base unit are given by powers of 10, and prefixes correspond to various multiples and fractions for all types of units. So you have a kilogram and a kilometer. That's what it's talking about in the last part. So they apply to different types of units. Now, we had a similar table to this in our notes from yesterday. We even chatted briefly when you guys were doing one of the examples about deca and deci. They're both D's, so they can't have abbreviation of both of them being D's. So deca has an abbreviation of DA. That's the prefix that you use. The factor that you're talking about is as it relates to the base unit. So if your base unit is, say, meters, just so that I can have something to reference. So if we're using meters, a kilometer is 1,000 meters. And a hectometer is 100 meters. And a decameter is 10 meters all the way down. So that's what those numbers on the right are. Is it's telling you the relationship that that value has back to meters or liters or grams. In fact, specifically, the next table is for metric length measurements because we're working on lengths in this section. Kilometers, hectometers, decameters, and so forth. And you see 1 kilometer is equal to 1,000 meters, and on. Now, I'll come back to the screen in a second, I promise. The way that I was doing this problem is called, and you might want to write this down just so that you, in case you see it somewhere else, and I'm not going to call it this, but if you were taking a certain kind of a test and it told you to do dimensional analysis, that might freak you out. This is called dimensional analysis. Okay? It's just a process by which to convert values. And we could do the metric conversions like this. We could do it. I mean, we could set them up this way. I can write 1,000 meters on top of 1 kilometer. I mean, we can do it that way. But we recognize that we don't need to because they're all powers of 10 and there's much easier to simply move decimal places. So we don't usually do metric conversions with dimensional analysis because it's simply not necessary. But you could. It would work. You'd get the right answers. One of the things that I'm interested in you doing at some point as we're working on the metric system is having some metrics in your mind of what things are equal to. Like, for example, when you guys measured from the doorknob down, do you remember about what it was? $70-something? Does that sound right? 70-something centimeters? I think you're measuring in centimeters. Taylor's looking hers up for her. What'd you get, Taylor?
99 centimeters.
99. So a little bit close. I was thinking it was close to the number 100, but I didn't remember for sure. No, so it's pretty much 100. Well, 100 centimeters is equal to what? 1 meter. So the doorknob down's about a meter. That's a really good reference point. There's another one in your book. If you take your shoulder to the tips of your opposite hand, it's about a meter. Okay, that's approximation because obviously my span right here is going to be different than like Russell Westbrook's, right? Okay, so this is going to be a standard measurement that's an approximation, but it gives you something in your mind to think, does that make sense? So if somebody told you that they had a baby and the baby was 76 centimeters long, you should look at them and say, are you sure that's the number you meant? Because that would be awfully long for a baby, right? You see what I'm saying? Like, our goal when we're looking at some of this too is to have reference points. Does something make sense? We haven't done weight But again, weight's one of those things. Like, you may know approximately that a baby weighs 7 pounds. So if somebody tells you that they had a baby and it weighed 5 kilograms, you should ask them, are you sure? Did you have that baby naturally? Because that doesn't sound quite right. That would be an over 10-pound baby. They exist, but it's not the norm, right? So these are the kind of reference points that we want. There's a couple others here too. A centimeter. If you take your finger and you look at your fingertip like where your nail is, the measurement across your finger is about a centimeter. That's a cool measurement to have. And the doorknob and this one, they're all really good to have because you see them all the time. I mean, how many times do you go through a door with a doorknob? Like forever. I mean, like all the time, right? It happens constantly. How many times is your shoulder to your fingertip available for you to kind of look at and go, yeah, I got that one? Or your fingers, right? They're there all the time. So those reference points are fantastic. A paper clip. Whether you have a paper clip available or not, you know what a paper clip looks like. They're used regularly. So the width of the prong of the paper clip is about 1 millimeter. All right, so we're going to do some examples reminding ourselves from last time, basically, converting within the metric system, okay? And we talked about how all we really need to do is move decimal places, and we had a fun acronym, although I think Sabrina's was more fun. We'll do it with the M, because if you want to. So we had King Henry, whoops, let me space them out just a little bit. King Henry died by drinking chocolate milk, and the by here is in meters. What was your M?
Monday.
Monday. He died Monday. Just so you know, he died Monday by drinking chocolate milk. All right, so we're going to measure, or we're going to count how far we're moving. So we're starting with 1.68 kilometers. So this is the 1.68 right here. And we want to turn it into meters. So I want to get back to the base unit. How many places would I have to move to the right to do that? Remember, you don't count where you are, you count the move to do that. How many moves would you have to make? 3. We're just going to meters. Meters is in the middle. Millimeters would be 6. Meters is in the middle. Yeah, it would be 3 decimal places, right? So I'm going to take my number 1.68 and you tack on however many zeros you want. You can tack on a bunch of them, but you just need to move the decimal 3 places. So here's 1, 2, and 3. So I don't really need these extra zeros here that I put on there. I end up with what? 1,680 meters. Now the next one is 973 millimeters. So on this one, I'm starting over here, 973, and I want to turn it into meters, which is back in the middle. How many places would I have to move? 3. But it's 3 in the opposite direction, right? It's 3 to the left. So when I write down 973, I know it doesn't really seem like there's a decimal point there, but you and I both know there is at the end. It's the place value, right? Like think money, $973.00. Zeros at the end like this. But I want my value to move to the left 3. So here's 1, 2, and 3. And if we needed, we could tack on extra zeros to keep moving. We don't actually need them here. So you can either write a decimal point and then 973, or if you want, you can write a 0 in front of the decimal point. Either way. So this would be 973 thousandths of a meter. And then this is just written slightly differently, but we're doing the same thing on part C, or part number 6 rather. We're going to go from the decimal point 0.42 kilometers to centimeters. So kilometers is over here again, 0.42. But now I want to go all the way back to centimeters, way over here. How many columns to the right is that? 5. So I've got to move my decimal point how many times? 5. Do I move it to the right or to the left? To the right, because centimeters is to the right of kilometers. So I have my decimal point 42, and I can put on, extra zeros like I said over there a minute ago. And like Tori and I both said, it was 5, right? Because you were the one talking to me. We're going to be at 5 times. So here's 1, 2, 3, 4, and 5. So I didn't need that many zeros. So what do I have for my number? Yeah, 42,000 centimeters. Okay? Any questions on that? All right. A few other things in this section about linear measure. It's about distances. We're going to talk about the triangle inequality. So triangle inequality says that the sum of the measure of any two sides of a triangle must be greater than the measure of the third side. This is equivalent to the statement that you've heard where it said before. It says the shortest distance between 2 points is a straight line. Yeah, you usually hear a straight line, but it's a line, right? Or you may have heard the distance from here to wherever as the crow flies. Has anybody heard that expression? It's an older person expression. It's not one I use, but as the crow flies would be that straight line, right? It's not the MapQuest thing. You don't Google Maps it, and they don't take you that way. So when we're going from one location to another one, it's always going to be longer if I take a route that's not straight. And so if I take this route, these two sides, or I go the straight route, I basically have two different options, and we can compare them in terms of a triangle. So any two sides of this triangle added together are going to be more than the third. That's what the triangle inequality says. So we're going to decide if the measurements given, I can leave that there, I guess, if the measurements that they give us actually are doable. Let me move it. For a triangle. So take a look at these numbers, 5, 7, and 13. Is it possible that this forms a triangle? No. Casey, why not? Right. This is a no, and the reason is because 5 plus 7 is 12. And 12 is not greater than the 13, right? There are two sides that when I add them together, it actually doesn't work. How about 5 and 8 and 13? No. Why not, Alicia?
Because it's equal to 30.
Right. So the 5 plus 7 equals 13, or sorry, 5 plus 8. My bad. The 5 plus 8 equals 13, so like it's closer to working, right, than the other one. But 13 is not greater again than 13. We need a greater number. So if the 8 had been a 9, we'd be good to go, right? But it wasn't. So 5, 8, 13 will not work either. Perimeter is a measurement that we use a lot. Sometimes people get perimeter and area confused. So we're going to do perimeter today. Perimeter of a simple closed curve is the length of the curve. The perimeter of a polygon is the sum of the side lengths, or the distance around the polygon. And this statement at the end, the phrase distance around, is, I think, for me, the most useful description of perimeter. It works for any shape, so to speak. I mean, if I'm talking about a shape that has a circular part to it, it's not actually a polygon, it'll still work because you still have a distance around a circle. We have another name we often use for that, circumference, but it's just a perimeter, right? It's just the distance around. So distance around is a good way to think about perimeter. Now we're going to do one for a triangle. First question is to find the perimeter of this triangle. So, what would I do? Yeah, I just add the side lengths. So I have 8, 10, and 12 for a sum of what? 30. Oh, and you even said centimeters. Bless your heart. That's wonderful. We need the units. This whole chapter is all about units. So if you write down 30 and you don't write down units, we've got a problem, because the whole point is that we're going to be doing a lot of conversions, all right? So make sure you get those units on there. I mentioned it already, but we're going to formally introduce it now, is the word circumference. Circumference is actually the perimeter of a circle. So in the picture, in the top right-hand corner here, the circumference is the black part around the object, whereas the radius, our next description, is the distance from the center to the circle's edge. We call this C, we call this R, and diameter, which we'll call D, I'll go ahead and write in. So the radius is the blue part of this on the circle. The diameter is the distance from edge to edge through the center. It's denoted D. And you should notice that D is twice what R is. Right? If the radius is halfway, right, it's from the center out, and I go all the way from the center out in both directions, I've got twice the radius. And I read you a book last time, and in the book we had the dragon of pi, and we talked about this number pi. And the number pi is a ratio of the circumference to the diameter. Right? We had a riddle there. All the circle around and then across the circle. And we often think about our formula as 2 pi r squared. I'm sorry, I'm not saying this right. I'm mixing up all my formulas. We often think of our formula for circumference as 2 pi r. You can also think of it as pi times the diameter. And of course, those are the same because the diameter is the same as 2 times the radius, which we already said. So either of these is a valid way for finding the circumference of your circle. We also could talk about just a portion of the circumference, like not the whole thing. We don't want to go all the way around. We just want to go part of the way around. Maybe you're talking about like how much crust there is on that pizza, right? That edge piece, that's what we're looking at. That's actually got a name, it's called arc length. So the length of the arc of a circle. The measurement in the middle, the angle that it creates, is called the central angle. So this is an angle whose vertex is at the center of a circle. The sides are the radii of the circle. And then the way that we can find the length of that piece along the edge, it's red on my diagram, is by taking pi r times theta over 180. And I would like to show you where that comes from because it's a very simple, it's very simple what you're doing to create it. R is the radius of the circle, theta is the measure of the central angle. The formula for circumference a moment ago we had written down was what? With the r in it. 2 pi r. And that is related to going all the way around the circle, right? I mean, it's the whole circle, so to speak. So if I were to think about that in terms of this diagram and I went all the way around, what angle measure would that create? It'd be a 360-degree angle. So this, as a ratio or a comparison, is the circumference 2 pi r compared to 360 degrees. This would be the whole way around my circle. And if I were to reduce this, I notice that the 2 and the 360 are both even, so they can be reduced. And I would reduce this to pi r over 360. I'm sorry, over 180, excuse me. So where did the theta come? Well, the theta is whatever angle that we have. Instead of the whole angle all the way around, we have only a portion of it. So our arc length TH, there we go, takes this ratio pi r over 180 and it multiplies it by the angle measure that we have, which is theta. Okay, so that's where it's coming from. It's really just a comparison of angle measure to circumference. All right. So we're going to take a look at some examples of this. Example number 8 says the following. If a circle has a diameter of 4/pi centimeters, what is its circumference? So because we're given the diameter, we might as well use the circumference formula that says d in it instead. So what is that formula? Yeah, pi d or d pi. And in this case, they tell us that the diameter is what? 4/pi. So what happens when you multiply pi by 4/pi? Yeah, you get 4. So this is equal to 4. Thank you. I was just looking back at my notes. 4 centimeters. Because the measurement for the radius was originally, or diameter was given in centimeters. Excuse me, if a circle has a circumference of 68 meters, what is its radius? Okay, so that's a little bit different. The last question asked us for finding the circumference, and in this question they tell us what their circumference is. How will I use the formulas that I have to be able to find the radius? Okay, so the circumference is 2 pi r is my formula, and our circumference, like you said, is the 0.68. So it looks something like that, right? Remember, pi is a number, so there's only one variable here. It's r. I should be able to solve for r. How would I do that?
Divide both sides by 2 pi.
Right. Divide both sides by 2 pi. Now you need to be a little bit careful with your calculator doing that. Your calculator, depending on what it is, may force you to put the 2 pi in parentheses. Otherwise it might divide by 2 and then multiply by pi. So you need to be a little bit careful. That's what my calculator would do. That's how it understands things. Not all do, but just be aware. What would you get then? Again, we're going to use 2 decimals of accuracy for an approximation for your radius. 0.11 what? Meters. Okay, did anybody's calculator not give them 0.11? I'd like for you to take a look so that you can know if your calculator is forcing with those parentheses or whether it doesn't care. I mean, how it's interpreting you as you enter it. So, Eliana, yours is going to need parentheses. Because you have what I have. I think, Tori, what do you have?
Yeah, actually.
Yeah, did you? It looked like it from here. Okay, does everybody get to the point, well, and Jillian as well, did everybody get to the point where you're getting an answer of 0.11? Is anybody not getting that answer when you're dividing? Okay, cool. So now you know how your calculator needs to have that entered. All right, number 10. What is the length of a semicircular arc of a circle whose radius is 1/2 inch? Now we could have drawn pictures on the last two, and that would have been fine, but they were pretty straightforward in terms of what they gave us. This one talks about a semicircle, though, and we didn't do anything with semicircles. So a circle or a diagram might help if you're having a difficult time picturing it. Here's a semicircle. It says the radius is 1/2, so I've got 1/2 for my radius. And it wants to find the length of the arc, right? Length of the arc. So what is the formula for arc length? Excellent. Now they gave us r. It was 1/2. What is theta? 180. How come? Yeah, it's a semicircle. So the arc that we're having right here, if you will, is 180 degrees. So I actually have a 180 right here. And since I have a 180 in the denominator, what do you think is going to happen? You could cancel them. You don't even have to, calculate that. And then basically we really just need 1/2 of pi. So what's 1/2 of pi? rounded to 2 decimal places.
1.57
1.57 inches. Cool. Last example. What is the radius of an arc, excuse me, whose central angle is 82 degrees and whose arc length is 160 centimeters? Again, if you want to draw a picture, by all means you can. This one is a little bit more direct because they give me the angle measurements, so it's like thinking through it is a little bit differently than the last one. It does ask for information about the radius, and it tells me something about arc length. So I'm going to start with that arc length formula that we had. And we'll take a look at what we have. So what can I plug in and where to that formula? 160 is L, right? What else? Okay, and theta is 82 degrees. So it should be that R is the only thing we don't know. Is that true? Good. There's a lot of ways to solve this. My best suggestion would probably be let's just multiply by 180 first and get rid of the fractional status of this. It should make the rest of it simpler to work with. So if I multiply by 180, of course the 180 in the numerator, or well, that I multiplied by and in the denominator will cancel. What's 180 times 160? Big. It's big, right? 28,800. And this equals 2, I'm sorry, not 2, pi r 82 degrees. What would I do next? We divide by 82. Can we divide by anything else? I would divide by 82 pi. It looks a lot like what we did at the last part of the other problem. So 28,800 divided by 82 pi. And what's the approximation we get with 2 decimals for our radius? .80 what? 85? Is that what everyone has? I have 0.8 as well. Couple of caution things. You might want to be careful. I don't know what you guys were doing. I guess I should have said it in case I didn't. Use the pi that's in your calculator. Don't use an approximation for it. So don't type in 3.14. Use the pi in the calculator. Yes, centimeters, thank you. And if you decide to get a number, like let's say over here on the the right-hand side, that you decide, I'm going to figure out what 82 pi is as a decimal and then use that, which you can, just keep a lot of decimal places to make sure you don't have any rounding problems too. It's another thing to be aware of. Okay, is everybody good with that? 111.80 centimeters. Alicia?
So I know why you multiplied by 180 on both sides,
Mm-hmm.
but could you also just pull R out? And then
Yes.
take that entire fraction?
Yes. Mm-hmm. Yeah, so her question is, could I, instead of multiplying by 180 and then dividing by 82 pi, could I have combined that into one step, basically? And yes, you can. Yeah. Just be careful with data entry in the calculator to do it. Mm-hmm. Eliana?
So if it's like a full circle, would the theta be 360?
It would. Yep. And in fact, if it were, then you would actually be finding circumference, technically. I mean, it is an arc length, but it would actually have another name as well, circumference. Yeah. All right.